Let's talk about how to convert cyclohexane that is drawn as this is really a 3D representation because the chlorine is wedge. This is called a wedge. So this right here is wedge and it's a bond, right? So the bond is wedge instead of just being a single line. This is dash. So the bond is these dash lines instead of just being a single line. You would have met solid and wedge before in when you looked at conformations, right? In your ring, whenever you have a wedge or a dash on a ring, it means something different from when you have it on a straight chain. On your ring, right, your dash means, your wedge, I'm sorry, means above the ring or pointing up. Above the ring or it's pointing up. Your dash means down, it's pointing, group is pointing down or below the ring. Now, when you're asked to convert um, a planar flat cycloalkane with substituents that are shown wedge and dash, when you're asked to draw the most stable chair conformation, this is how you approach that particular question. Draw your two chair conformations. If you have forgotten, go back to drawing chairs. It's those parallel lines. Draw the two set of parallel lines, right? I already drew the chairs. Now, this is what you do next. Your chlorine, your chlorine is wedge, which means it's above the ring, which means that whenever you put it on your chair, you need to put it in the position that is up or above the ring. Okay? Up and above the ring is the same place. All right? So wherever you put your chlorine on this ring, nobody cares. It's your ring. You decide what you want to do. You know I love the nose, so I'm going to stay on the nose, right? The key is wherever you put chlorine, CH3 is right next to it, right? In whichever direction you want. So for example, like I said, I like the nose. My Where these two lines meet, if you have forgotten pointing, they meet pointing down. So my axial bond here points down. And if the axial bond points down, then the equatorial bond points up. Put those two bonds on, right? This is where I'm going to put my chlorine. My chlorine is above or up, okay? The only bond here that is up or above the ring is the equatorial bond. So this is my axial bond down. This is my equatorial bond that is up. Okay, the only bond up here is this bond. So I'm going to go ahead and I'm going to put my Cl in the up position because the first thing we're doing is I am drawing the two chair conformation. You draw the two chairs, cool, with nothing on it. But then my goal is to draw the most stable chair conformation of this. So now I have to convert this thing into a chair conformation. Once you do it for this chair is literally a flip. Okay? So let's convert this into a chair conformation. You could have started over here, it's fine, right? The goal is when you flip the chair, you need to know where your groups are. So I have my Cl, I'm going to put my hydrogen in. Now pay attention, your CH3 is right next to, it's bonded to the carbon that is right next to the Cl. So your CH3 is on the carbon that is right next to the Cl, which means here's my Cl. I can put my CH3 either here or I could put it here. It doesn't matter. It would still be 1, 2. Okay? So I am going to put it here. So my CH3 is down or below. Let's first put the bonds. Actually, I think I'm gonna put it up here. Easier to see when I draw it. So your CH3 is down or below the ring, okay? So let's put in the bonds here. Your axial bonds point straight up on this carbon and the equatorial point down. So my CH3 needs to be down, okay? The only bond between these two that is down is this one, which means my CH3 is here, my hydrogen is here. I'm not going to put in the rest of the hydrogens. We don't need to. So my chair conformation, one of my chair conformations for this particular molecule is this. Okay, you don't have to sweat and be like, oh my God, how do I draw the second chair conformation? Once you do what I taught you to do when drawing chairs, which is just draw the two chair conformation, the only other chair conformation is going to be this one. Okay, now remember what happens when the chair rotates, right? If you are axial, you become equatorial. If you're up, you stay up. If you're down, you stay down. Don't forget that. So your chair, let's look at our chair. This is carbon 1, 2, 3, 4, 5, 6. My chair rotated this way, right? Because here's my nose. That's my nose. It moved up. So this is 1, and the chair moved in this direction. That's 1, 2, 3, 4, 5, 6. All right, cool. Now, on carbon 1, right, my CL is up and it's equatorial, which means when the chair flips, the CL stays up, but this time it's axial. All you have to do first thing, put the bonds on this carbon here. So let's put our bonds in. The axial bond will point up here because the lines meet pointing up, and the equatorial bond is down. So I know my CL is equatorial up here, right? If it's up, it's going to stay up, but instead of equatorial, it becomes axial. And if you follow the direction in which the bond points, remember where the line meet is where it shows you the direction in which the axial bond points, right? And just remember, axial become equatorial. Okay, choose something to remember. Choose that it stays up, or remember axial become equatorial. Pick one. All right. Now, carbon number 2 is right here. On carbon 2, okay, my CH3 is down, equatorial. The hydrogen is axial up. So over here, let's put our bonds in. The axial bond is the one that will point down here, right? Because these two lines meet pointing down, in case you have forgotten. The equatorial bond will point up, okay? And that looks over. So that's up, and this is axial down. So here is my carbon 2. My CH3 is down, equatorial. So on carbon 2 here, I need to place my hydrogen. It needs to stay down, and it is axial. So CH3 is here, and here's my hydrogen. Now the question asks you to draw the most stable chair conformation of this thing, all right? So we've completed the first part. We've drawn the two chair conformation of this molecule, right, given the structure. Now let's examine our chair to see which one is more stable. Ding, ding, ding. What did I tell you you need to remember if you're asked about the stability of chair? I hope you're screaming behind the screen. 1,3 diaxial interaction. 1,3 diaxial interaction. So let's look at what we have. Here, I have a Cl. So you look for the groups that are not hydrogen. I hope you remember that. Here, we have a Cl. Here, we have a CH3. But guess what? They're in the equatorial position, both of them, right? So there is no 1,3 diaxial interaction in this chair. If we come over here, right, I'm going to call these chairs A, chair B. If I come to chair B, right, I have my CL is axial. My CL is in the axial position, and guess what? My CH3 at the bottom of the ring is also in the axial position. You can have 1,3 diaxial interaction at the bottom and at the top. So this molecule has 1,3 diaxial interaction. It has 1,3 diaxial interaction. Let's find it. So this is carbon. This is the carbon with the Cl. Let's go 3 carbons away. The hydrogen that is in the axial position here So my hydrogen here in the axial position is what the chlorine will have the 1,3-dioxyl interaction with. If we go um, 1,3-dioxyl interaction, so 3 carbons away from the chlorine in the other direction, I also have axial hydrogen, that's 1, 3. So I have a HCl steric interaction, repulsion, right? Because it's the electrons repelling each other, times 2. But also realize downstairs, I also have a CH2 in the axial position. You can have axial 1,3-dioxyl interaction below the ring. Let's show you. So here we go. Let's pick um, this blue. So here's my there's my CH3. Let's do 3 carbons away in this direction, right? On this carbon, I have my hydrogen. That's in the axial position pointing down, equatorial. And how I knew it was axial, don't forget where the lines point. So I can have 1,3-dioxyl interaction between this CH3 and this hydrogen at the bottom of the ring in the axial position. If you look at the model that I had earlier, you will see that the 3 axial bonds at the bottom, they're in a position where they can interact. Let's look at, wait, sorry, my bottom carbon. Okay, I looked at the top. So here we go. Let's look at our 1,2-dioxyl interaction. So 1,2-dioxyl interaction at the bottom is the blue. Let's look at our 1,2-dioxyl interaction on the other side of the ring. So 1, 2, 3. Our hydrogen on this carbon, axial position. So this CH3 can interact with this hydrogen in the axial position. All of this is happening at the bottom. So we have a CH3 hydrogen steric interaction. The electron clouds are repelling each other 2 times. This chair right here is very, very unstable compared to this one, right? There's no 1,3-dioxyl interaction here. There's no chaos. There's no repulsion of electron clouds. But in the axial position here, we have this going on at the top and we have it going on at the bottom. So your most stable chair, right, is going to be this chair right here. That's your most stable chair. Okay. So if you get a question like this, you shouldn't struggle. Let's look at, okay, so for you, go ahead and try this one on your own and go ahead and just try it on your own and let me know what position this group is in and this group is in, if it's in the axial or the equatorial for the more stable chair conformation. I'm going to do another example using a flat structure that has 2 groups that are on the same side. Okay, so let us do this molecule. All right, so remember your dashed lines mean that, and by the way, sorry, ET is your ethyl group and ME. So if you ever see these, you don't need to be scared. It's ethyl and methyl. Okay, so the question is, what is the most stable chair conformation of this molecule? Okay, the first thing you're gonna do is you need to draw your 2-chair conformation, right? Because it's one of those that is the more stable. That's why you do that. You don't have to sweat, just draw it. Draw the 2-chair conformation. Remember how you draw them: parallel lines, slightly, not directly under each other. Then you draw your second chair with your parallel lines in the opposite direction, right? So these are my 2 chairs, all right? Now, I'm gonna convert this from this 3D structure because this is showing that it's below the ring. You can call it's showing stereochemistry, right? Below the ring, below the ring. I'm going to convert this into a chair conformation. Okay, and remember, you can place this group anywhere on the chair. The only thing is you have to make sure that wherever you put ME is 3 places away from this. Okay, I love the notes, so I'm going to stay there. So let's do this and move this chair over a little bit. So here we go. On this carbon, I have a axial group pointing straight down, equatorial group pointing straight up. So if we look at my structure here, this ethyl group is below the ring or down, okay? So here I need to put my ethyl below the ring. The only bond below the ring here is my axial bond. So this is that. This is axial. The equatorial bond is up, right? And I'm putting my hydrogen on it. Now 3 carbons away, right? And you can go in any direction. I could have chose to go 1, 2, 3, but you know I like staying on the nose or the tail. So I'm gonna put the methyl group here. So on this carbon, I know my axial bond points straight up, equatorial bond points, sorry. On this bond, I know my axial bond points straight down, equatorial bond points straight up. How did I know that? Don't forget, wherever the lines meet, pointing is where the axial bond point. And if the axial bond is down, the equatorial bond is up. All right. So I have methyl, I'm sorry, I'm at methyl, and it's below the ring, right? Below the ring or down. The only bond here that is down is the axial bond. So Me has to be here. All right, cool. Now, let us number our carbon so I can see what direction the chair rotated in, right? So if you notice, here is my nose for this chair and stay on the right. On the right over here, the nose went up. Nose down. Over here, the nose went up. So it means that my chair rotated this way, right? So my chair rotated in that direction, which means now that this is my new carbon one. And since the chair is moving this way, this is 6, this is 5, this is 4, 3, 2. All right. So remember what happens when the chair rotates, yes? So on carbon one, since my chair rotated, carbon one here, my hydrogen, let's focus on the most important group. My ethyl group is down and in the axial position. So it means when I come over here, my axial bond points straight up, equatorial bond points straight down. From here, my ethyl group is down, axial. So it means it's gonna stay down over here, but it's gonna be equatorial. And you don't even have to sweat. The only bond down here is the equatorial bond. So you get this hydrogen. All right. Then my carbon 3 is right here. Let me put the bonds in. Since the line meet pointing up, your axial bond is up on this carbon, equatorial is down. So let's go to carbon 3 over here because I need to know what happened when my chair rotates. Me is in the axial down position, which means when it comes over here, it needs to stay down and it becomes equatorial. So Me is here and your hydrogen is here. So now we have chair A and chair B. All right. Now, again, if I ask you the question, which one of these chairs are more stable, what are you looking for? 1,3-diaxial interaction. I have an ethyl group in the axial position and a methyl group in the axial position, right? You can have 1,3-diaxial interaction at the bottom of the chair between these two things, right? And then the methyl will have 1,3-diaxial interaction with the hydrogen here in the axial position. And then this, if you move in this direction, it will have an interaction here. So you have Me to E, T interaction. Then you have Me interacting with the hydrogen and you have Et. What a lot of repulsion. So this chair, for sure, right? This chair has 1,3-diaxial interaction, right? And it has a lot of it, okay? So a lot of repulsion, a lot of chaos. Let's move over to B. B, my groups that are not hydrogen are not in the axial position. For 1,3-diaxial interaction, it's in the name, it must be in the axial position. These are in the equatorial position. So ding, 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 ding. Guess which chair is the most stable? This is your most stable chair. Now you're a pro. You can answer these questions.